Right now, surrounding our entire solar system, there is a shell of frozen objects, 1 trillion strong. Most of them have never moved. Some have been sitting still since before Earth existed. We call it the Oort cloud, and for 75 years, scientists thought they understood it. A quiet, frozen bubble. Boring. They were wrong. It has spiral arms, it holds material from other stars, and the entire galaxy is slowly stirring it. We will visit a comet the size of Los Angeles, already waking up far past Neptune, a world sitting in a region no planet can touch, and a discovery that happened by accident inside a planetarium. If you enjoy the journey, subscribe and leave a like. Prepare yourselves. We begin. Picture the solar system as a city. The sun is downtown, Earth is a few blocks out. Neptune, the last real planet, sits about 30 blocks away. And then, nothing. Just open road, stretching on for thousands of miles, with no buildings, no lights, no signs of anything. Except there is something out there. Way past Neptune, in the cold and the dark, sits one of the largest structures in the solar system. A shell of frozen objects so vast, it wraps the entire city in a bubble the size of a continent. Scientists call it the Oort cloud. And almost no one talks about it. The name sounds soft. Cloud, like something fluffy and harmless floating over a summer afternoon. The reality is nothing like that. The Oort cloud is a graveyard. A deep freeze holding the leftover wreckage from the formation of our solar system 4.5 billion years ago. Chunks of ice, frozen gas, and rock, some as big as mountains, some the size of a house, all suspended in near total darkness, barely moving, barely warmed by a sun so far away it looks like just another star. Here is the number that matters. 1 astronomical unit is the distance from Earth to the Sun. About 93 million miles. Neptune, the farthest planet, sits 30 of those units out. The Oort cloud begins somewhere between 2,000 and 5,000 units from the Sun, and it stretches outward to somewhere between 100,000 and 200,000 units. Put that in human terms. If Neptune were 1 inch from the Sun, the outer Oort cloud would be over a mile away. 1 mile. That is how alone those objects are. And here is the strangest part of all this. No one has ever actually seen the Oort cloud. No telescope has photographed it. No probe has visited it. Every single thing scientists know about it comes from math, from computer models, and from watching what falls out of it when something nudges an icy body loose and sends it tumbling toward the sun. We know it exists because of its fingerprints, and those fingerprints are comets. Every few years, a long-period comet blazes through the inner solar system. These are the dramatic ones, bright enough to see from Earth, trailing glowing tails millions of miles long. Scientists trace those orbits backward, calculating where the comet came from before it fell inward. Almost every long-period comet traces back to the same distant region, the same frozen shell. The Oort cloud announces itself through every comet that reaches us, even though we have never seen its face directly. The objects sitting out there right now have been frozen since before the first dinosaur, since before the oceans formed. They are pristine, untouched, chemical time capsules from the birth of everything in this solar system, and most of them will stay out there forever. Quiet, cold, invisible, but some get nudged. Something pushes them, and when they fall, they carry 4.5 billion years of history directly into our sky. The question scientists spent decades trying to answer was, how did they get out there in the first place? The answer is wilder than anyone expected, and it starts with a catastrophe. In 1950, a Dutch astronomer named Jan Oort sat down with a list of 19 comets. He was trying to solve a puzzle that had bothered scientists for decades. Comets burn. Every time one swoops close to the sun, it loses material, venting gas and dust into space. After enough passes, it runs out. So where do new comets keep coming from? Something had to be replenishing the supply. Something far away. Oort did not have a telescope powerful enough to see it. He had something better. He had math. He took those 19 comets and worked backward. Using the physics of gravity, he calculated the original orbit each comet had before it ever entered the inner solar system. He wanted to know where each one came from, not where it was now, but where it started. 10 of the 19 came from roughly the same enormous distance, tens of thousands of astronomical units from the Sun, far beyond any planet, far beyond anything mapped at the time. One comet from that distance would be a coincidence. Two would be interesting. 10 out of 19, that was a pattern. That was evidence. But Oort noticed something even stranger. These comets were arriving from all directions, some from above the solar system's flat plane, some from below, some from the side. If the source were a flat disk like the ring of objects we now call the Kuiper belt, all the comets would arrive clustered along that same flat plane. The fact that they came from every angle meant the source had to be a sphere, a shell surrounding the solar system in all directions equally. He published his findings in 1950 and proposed the existence of a distant, roughly spherical reservoir of icy objects. He estimated it held enormous numbers of bodies. He described the shape, the approximate distance, and the mechanism by which comets escaped from it, all from 19 data points and a pencil. Scientists had not seen it. They still have not seen it. But the logic was airtight. The comets themselves were confessing where they came from, and Oort was listening. His calculation has held up for 75 years. Every major revision since then has added detail to his picture. But the core idea, a spherical shell of icy objects at the outer edge of the solar system, has survived every new telescope, every new computer model, every new discovery. One man, one list, one pattern. And he mapped the largest structure in the solar system without leaving his desk. 17 years earlier, an Estonian astronomer named Ernst Öpik had made a similar suggestion, reasoning in 1932 that comets must come from a distant reservoir to explain why the supply never runs dry. But it was Oort who built the full model, put real numbers to it, and convinced the scientific community. The cloud carries Oort's name today, and for most of the following decades, scientists thought his original picture was basically complete. A quiet, symmetric shell, stable, featureless, boring. They were working with incomplete information, because in 2025, a supercomputer revealed something hiding inside Oort's cloud that no one had imagined. A structure so unexpected that the scientist who built the simulation initially thought his own software had made a mistake. And the story of how that discovery happened starts in a planetarium of all places. You cannot take a photo of the Oort cloud. You cannot point a telescope at it and watch it sit there. Every confirmed Oort cloud object is invisible from Earth, too small and too far away to reflect enough light for any instrument we have ever built. So how does science actually confirm it exists? The answer comes down to orbital mechanics, the physics of how objects move through space under the influence of gravity. And it is one of the most powerful tools in astronomy because it works in reverse. If you know where something is and how fast it is moving, you can calculate exactly where it came from and where it is going, even if you never saw it at the start. Every comet that enters the inner solar system carries its entire travel history locked inside its orbit. Scientists measure the comet's position, its speed, and its direction. They feed that into the equations, and the equations unspool the path backward, tracing the comet's journey across tens of thousands of astronomical units, back to the place it called home before something knocked it loose. Do that calculation for enough comets, and a pattern emerges. Long-period comets, the ones that take thousands or even millions of years to complete a single orbit, all point back to the same enormous distant region. They come from a shell wrapped around the entire solar system. Every time a new long-period comet appears, scientists trace it back, and it confirms the same picture. The Oort cloud is out there. There is another piece of evidence that is even harder to argue with: the distribution of the directions those comets come from. If you plot where long-period comets arrive from on a map of the whole sky, they spread out in all directions with remarkable evenness, up, down, sideways, from every angle. That distribution is the fingerprint of a spherical source. A flat disk would produce comets clustered along a line. A lopsided cloud would produce a bulge in one direction. A perfect sphere produces exactly what scientists observe: comets arriving from everywhere with equal probability. The math does not just confirm the Oort cloud exists, It describes its shape with precision, purely from the behavior of the objects that fall out of it. This kind of indirect proof sounds like it should be less convincing than a photograph. But in science, orbital mechanics is considered ironclad. The same math that lets engineers navigate spacecraft to Pluto with inch-level accuracy over 3 billion miles of travel is the same math that traces comets back to the Oort cloud. The precision is extraordinary. There is something almost haunting about this. 1 trillion objects sitting in the dark, completely invisible, completely unreachable, silently proving their own existence every time one of them falls inward and lights up our sky. The Oort cloud announces itself with every spectacular comet humanity has ever watched streak overhead. From ancient civilizations reading them as omens, to modern scientists watching them through space telescopes. All of it, every bright tail, every dramatic plunge toward the sun, is a message from the outer edge of our solar system. And those messages have been consistent for 75 years. But the message that arrived in early 2025 was something else entirely. Something the math revealed that no one had been looking for. Stand on Earth. The sun is 93 million miles away. That distance, 1 astronomical unit, is the baseline scientists use to measure everything else in the solar system. Mars is 1.5 units out. Jupiter is 5. Saturn is 10. Uranus is 19. Neptune, the last of the 8 planets, sits at 30 units. Beyond Neptune, the solar system keeps going, a scattered field of smaller objects called the Kuiper Belt, stretching out to maybe 50 or 60 units. Then there is a gap, a long, mostly empty stretch. And somewhere between 2,000 and 5,000 units from the Sun, the Oort cloud begins. To cross the gap between Neptune and the inner edge of the Oort cloud, you would travel a distance roughly equal to 66 times the distance from Earth to Neptune. In miles, that is somewhere around 150 billion miles of near empty space. Here is a way to feel that distance. The fastest spacecraft humans have ever launched is Voyager 1. It has been traveling since 1977 and covers about 1 million miles every single day. To cross from Neptune's orbit to the inner edge of the Oort cloud, Voyager would need over 400 years of continuous travel. And that is just to reach the starting line of the Oort cloud. The cloud itself extends outward for another enormous distance, eventually reaching somewhere between 100,000 and 200,000 units from the Sun. At the outer edge, you are roughly 3 light-years away from the Sun. A light-year is about 6 trillion miles. At Voyager's speed, reaching the outer edge of the Oort cloud from Earth would take over 30,000 years. The Oort cloud does not begin where our solar system ends. It begins where the Sun's gravity starts to lose its grip. Close to the Sun controls everything. Its gravitational pull dominates all motion within the planetary system. Farther out, that grip weakens. By the time you reach the inner Oort cloud, the Sun's gravity is so faint that the gravitational tug of the entire Milky Way galaxy starts to compete with it. That boundary, where the Sun stops being the dominant force and the galaxy takes over, is where the Oort cloud lives. It occupies the space between our solar system and the rest of the universe. A transition zone between everything we know and everything beyond. Objects sitting at the outer edge of the Oort cloud are barely bound to the Sun at all. They feel the Sun's gravity like a whisper, a passing star, a nudge from the galactic tide. Even the gravitational pull of a distant molecular cloud can push them off their paths and send them falling inward over thousands or millions of years. That is why the Oort cloud is a source of comets. Its objects are loosely held. They are easy to disturb. And in 2025, scientists discovered what has been disturbing them all along. In 2012, NASA confirmed that Voyager 1 had crossed the heliopause, the boundary where the Sun's outward flow of particles finally gives way to the interstellar medium. Scientists celebrated. Humanity's first object to reach interstellar space. Every headline called it the edge of the solar system. Here is what those headlines missed. Voyager 1 is inside the Oort cloud's future path by a wide margin. The inner boundary of the Oort cloud sits somewhere between 2,000 and 5,000 astronomical units from the Sun. In 2025, Voyager 1 is somewhere around 160 units out. It has not even covered 10% of the distance to where the Oort cloud begins. At its current speed of roughly 38,000 miles per hour, Voyager 1 will not enter the Oort cloud for approximately 300 years, and once it enters, it will take another 30,000 years to pass through the other side, 300 years to arrive, 30,000 years to cross. Voyager 1 launched before the personal computer existed. It will enter the Oort cloud long after every living human is gone. It will exit the Oort cloud so far in the future that human civilization, if it still exists, will have had time to rise and fall and rise again many times over. That is the scale of what we are dealing with. And yet the Oort cloud still belongs to our solar system. It is still gravitationally tied, however loosely, to the Sun. Its objects still orbit the Sun, even if those orbits take tens of millions of years to complete. The cloud is the Sun's outermost territory, the very farthest reach of its gravitational influence, stretching from the boundary of the planetary system almost halfway to the next nearest star. Proxima Centauri, the closest star to our Sun, sits about 4.2 light-years away. The outer edge of the Oort cloud reaches to about 3 light-years. Our solar system's frozen shell extends almost 3/4 of the way to the nearest neighbor. Think about what that means for the neighborhood. If the Oort cloud around our Sun reaches 3 light-years out, and Proxima Centauri has its own similar cloud, and the distance between them is 4 light-years, those two clouds nearly touch, the frozen outer edges of two separate star systems, brushing against each other in the dark. Scientists suspect this is already happening. The implications are significant, and they connect directly to one of the strangest discoveries about the Oort cloud in decades, where some of its material actually came from. Because a growing body of research suggests that a meaningful fraction of the objects sitting in our Oort cloud right now did not form around our Sun. 4.5 billion years ago, the solar system was a war zone. The Sun had just ignited. Around it spun a vast disk of gas, dust, and rock, the raw material for everything that would eventually become the planets, moons, comets, and asteroids we know today. The outer part of that disk was cold enough for water, carbon dioxide, methane, and carbon monoxide to freeze solid. Billions of icy chunks began clumping together, growing larger over millions of years, building the cores of what would become the outer planets. But the outer planets, Jupiter and Saturn especially, grew enormous. And enormous planets are gravitational bullies. As Jupiter reached its full size, its gravity started flinging the smaller icy objects around it at tremendous speed. Some got launched into the inner solar system, some got captured into stable orbits, and billions of them got thrown outward, toward the edge of the solar system and beyond. This was the event that built the Oort cloud. The planetesimals hurled outward by Jupiter, Saturn, Uranus, and Neptune traveled billions of miles in elliptical arcs, stretching far from the Sun. Most of the objects thrown by Jupiter were ejected so violently they left the solar system entirely, gone forever into interstellar space. The ones thrown by the more distant ice giants, Uranus and Neptune, were launched with less force. They traveled far, but stayed bound to the Sun. Once they reached the outer solar system, something else took over. The galactic tide, the combined gravitational pull of all the stars, gas, and dark matter in the Milky Way galaxy, began acting on these distant, loosely bound objects. Over millions of years, the galactic tide pulled and pushed at their orbits, lifting the closest points of their paths away from the planetary zone, and gradually rounding out their orbits into the near-circular paths we see today. The result was the Oort cloud, a graveyard of construction debris from the building of the outer planets, pushed to the edge of the solar system and gently rounded into a shell by the slow pull of the galaxy. The bulk of the Oort cloud, roughly 70% of it by mass, originally formed in the region between 15 and 35 astronomical units from the Sun. That is the neighborhood of Uranus, Neptune, and the family of smaller icy bodies called centaurs. These objects were born in the thick of the solar system's most violent era and carried the chemistry of that era locked inside them ever since. Frozen, preserved, waiting. But here is where it gets complicated. Scientists assumed for decades that everything in the Oort cloud came from our solar system, that all those icy bodies were native, formed from the same gas cloud as the Sun. That assumption turned out to be wrong. Most people think of the Oort cloud as one thing, a single bubble wrapping the solar system in a uniform shell. The real structure is more complicated than that, and the difference matters enormously. Scientists divide the Oort cloud into two regions with fundamentally different shapes, different histories, and different behavior. The outer Oort cloud is the part that matches the classic picture. It is a roughly spherical shell, extending from somewhere around 20,000 astronomical units out to somewhere between 100,000 and 200,000 units. Objects here orbit the Sun from every direction, above, below, and sideways relative to the flat plane of the planets. Their orbits are scrambled, pointing every which way, because the galactic tide and passing stars have had billions of years to stir them up and randomize their paths. This is where most long-period comets originate. When something disturbs this outer shell, objects can fall inward and take anywhere from thousands to tens of millions of years to make one trip around the Sun. The inner Oort cloud is different. Scientists sometimes call it the Hills cloud, after astronomer Jack Hills, who proposed its existence in 1981. It sits between roughly 2,000 and 20,000 astronomical units from the Sun. It is denser than the outer cloud. It holds more objects, and rather than a sphere, it has a flattened, disc-like shape tilted about 30 degrees from the plane of the planets. The inner cloud is harder to disturb than the outer cloud. Objects there are closer to the Sun, so the Sun's gravity holds them more firmly. Random passing stars rarely reach them. The galactic tide works on them, but more slowly. For decades, that was the full picture: a spherical outer halo and a denser inner disk. Two zones, different shapes, both basically featureless. Then, in February 2025, a team running one of the most detailed Oort cloud simulations ever built found something inside the inner cloud that shattered the featureless picture entirely. The inner Oort cloud has arms, spiral arms, two of them twisting through the inner disk like the arms of a miniature galaxy, stretching roughly 15,000 astronomical units from tip to tip. The scientist who led the simulation initially thought his software had created a visual error, a glitch, an artifact of the way the data was being drawn on screen. He checked the physics. He ran the model again. The spiral was real. And the story of how anyone noticed it at all begins in a building in New York City, in the middle of a show about the Milky Way. In February 2025, a paper landed in the astronomy community with the weight of a discovery no one had been looking for. A team led by planetary scientist David Nesvorny at the Southwest Research Institute published a simulation of the inner Oort cloud, so detailed and so carefully built that it revealed something completely unexpected, embedded in the physics of the model. The inner Oort cloud has two spiral arms. They stretch across roughly 15,000 astronomical units. They twist together like a double helix, tilted about 30 degrees from the plane of the planets. The structure is enormous, ancient, and physically stable. According to the simulation, the spiral arms formed within the first few 100 million years of the solar system's existence, and they have survived every stellar flyby, every galactic nudge, every gravitational disturbance across 4.5 billion years. They are still there today. The simulation was built using orbital data from known long-period comets and gravitational force parameters from inside and outside the solar system. The team ran the model on NASA's Pleiades supercomputer, one of the most powerful research machines in the world. The output was a three-dimensional map of where inner Oort cloud objects should be distributed today, given 4.5 billion years of gravitational evolution. When they visualized that map, the spiral jumped out. The mechanism driving the spiral is the galactic tide, the combined gravitational pull of the entire Milky Way galaxy. Billions of stars, clouds of gas, black holes, and dark matter acts on the loosely bound objects in the inner Oort cloud in a systematic, organized way. The vertical component of that tidal force pushes and pulls at the orbits of these objects in a pattern that correlates their positions over time, producing the twisted, arm-like structure. This is confirmed science. The paper was published in the Astrophysical Journal, a peer-reviewed journal, and the physics behind the spiral are grounded in well-understood gravitational dynamics. But what makes this discovery remarkable is its implication for our picture of the solar system. For 75 years, the Oort cloud was described as a featureless reservoir, uniform, random, a statistical blur. The 2025 simulation replaced that picture with something that looks, from the outside, like a tiny version of the Milky Way itself, a galaxy within a galaxy, wrapped around our sun. The spiral arms are not visible. No telescope can see them. They exist only in the physics and in the simulation that faithfully follows that physics. But they are real, and they have been there since the solar system was young. And the way they were discovered is one of the stranger stories in recent science. The discovery of the Oort cloud's spiral structure did not begin with a focused research project. It began with a ceiling. In 2024, the American Museum of Natural History in New York was developing a new planetarium show called Encounters in the Milky Way. The show needed to visualize the solar system's motion through the galaxy over vast timescales. To do that accurately, the production team pulled in data from David Nesvorny's comet simulation, which modeled the positions of inner Oort cloud objects as they evolved over billions of years under the influence of gravity. They projected that data onto the planetarium dome, and on the curved ceiling of the Hayden Planetarium, something appeared in the visualization that no one expected. A spiral, two arms twisting through the inner Oort cloud, unmistakable in the projection. Planetary scientist Jacqueline Faherty was part of the team developing the show. She saw it on the dome and contacted Nesvorny directly. Nesvorny's first reaction was doubt. Visualizations can produce visual artifacts, patterns that appear in the image due to the way data is being drawn, but do not correspond to real physical structures. He assumed that was what he was looking at. He went back and examined the simulation carefully. He checked the physics. He looked at what the model was actually computing, not just how it was being displayed. The spiral was embedded in the physics. It was a real structure predicted by the gravitational forces the model was tracking. Nesvorny confirmed it himself. The spiral had a solid physical rationale. The galactic tide, applied consistently over billions of years to the inner Oort cloud, naturally produces this pattern. It is not a coincidence. It is a consequence. Faherty described Nesvorny's simulation as firmly based on physics, and the spiral as a genuine feature of that physics made visible. The study was published in the Astrophysical Journal, one of the most respected publications in astronomy. It stands as one of the biggest revisions to the Oort cloud model since Jan Oort first proposed the cloud's existence in 1950, a structure that has been physically present for 4.5 billion years. Surrounding our solar system the entire time humanity has existed was first noticed because someone projected a comet simulation onto a domed ceiling for a public science show. Science works in unexpected ways, and the force responsible for that spiral, the galactic tide, is stranger and more powerful than most people realize. Gravity from the sun holds Earth in orbit. Gravity from Earth holds the moon. Most people understand those relationships because the objects involved are close enough to feel concrete. The galactic tide is harder to picture, and it is one of the most important forces shaping the outer solar system. Every object in the Milky Way exerts gravitational pull on every other object. Billions of stars, enormous clouds of gas, dust spread across hundreds of thousands of light years, black holes scattered throughout the galaxy, and dark matter, the invisible mass that outweighs all the visible material combined, all of it pulling in all directions, all at once. For objects close to the sun, all of this distant galactic mass barely matters. The sun's own gravity is so much stronger that the galactic tide gets buried underneath it. Earth does not feel the Milky Way tug it around. The sun's pull completely dominates. But go far enough out, and that changes. In the inner Oort cloud, at distances of thousands of astronomical units, the sun's gravity is weakened dramatically with distance. The galactic tide starts to become comparable, and in the outer Oort cloud, at distances of tens of thousands of astronomical units, the galactic tide is a major player in shaping how objects move. The galactic tide has two main components. One pulls vertically, pushing objects above and below the flat plane of the galaxy. The other pulls horizontally, acting across the plane. Together, they steadily twist and reshape the orbits of Oort cloud objects over millions and billions of years. The vertical component is the key to what it does. When objects in the inner Oort cloud have their orbits tilted by the vertical galactic tide, the closest point of their orbit to the Sun gets raised or lowered systematically. Over time, this can push objects deeper into the outer cloud or pull them inward toward the Sun, where they eventually become visible as long-period comets. This was not just theorized. In 1987, scientists analyzed the orbits of 152 known long-period comets and found a clear pattern. The points in those orbits farthest from the Sun were systematically avoiding both the galactic poles and the galactic equator. That distribution matches exactly what the galactic tide predicts. The tide's fingerprints were visible in real comet data from over a century of observations. The galactic tide sculpts the Oort cloud the way wind shapes sand dunes, slowly, continuously, over timescales so enormous they barely register against a human life. And it is the same force responsible for the spiral structure discovered in 2025. The galactic tide, applied systematically over billions of years, organized the inner Oort cloud into those two twisted arms. But the galactic tide is not the only outside force acting on the Oort cloud. Something even closer and more personal occasionally reaches in and stirs things up. The inner Oort cloud does not sit flat. It does not line up with the plane of the planets. It does not align with the plane of the Milky Way galaxy. It sits tilted, at roughly 30 degrees from the plane of the solar system, pointing in a direction that cuts between the two flat planes at an angle. That tilt is not a random accident. It is a direct result of the geometry of the forces acting on it. The solar system's flat plane, called the ecliptic, is the plane in which the planets orbit the Sun. The Milky Way galaxy has its own flat plane, where most of the stars, gas, and dust are concentrated. These two planes are tilted relative to each other. The solar system is currently inclined about 60 degrees from the galactic plane. The galactic tide acts on the Oort cloud objects in a way that is tied to the geometry of the galactic plane. The vertical component of the tide, the part that pushes objects up and down relative to the galaxy, creates a preferred direction. It organizes the orbits of inner Oort cloud objects around an axis that is perpendicular to the galactic plane. The result is a disk and spiral structure that sticks out from the solar system's own plane at roughly 30 degrees, oriented in a specific direction dictated by the galaxy's gravitational geometry rather than the planet's geometry. The inner Oort cloud is not a child of the solar system's flat disk, it is a child of the galaxy. This is confirmed science, embedded in the physics of the 2025 simulation, and consistent with prior theoretical work on galactic tidal forcing. What makes the tilt significant is what it tells us about who is really in charge out there. Inside the planetary system, the Sun dominates. The planets orbit in a flat disk because of the original rotation of the gas cloud that formed the solar system. The inner Oort cloud's tilted geometry shows that past a certain distance, the Sun loses its authority. The galaxy takes over. Our solar system is not truly self-contained. It lives inside the Milky Way, and the Milky Way reaches in and reorganizes its outermost structures according to its own rules. The 30-degree tilt is the visible proof of that relationship. Every comet that falls toward the Sun from the inner Oort cloud carries the geometry of the galactic tide in its original orbit. There is still one number that scientists cannot fully explain. Why 30 degrees specifically? The simulation produces it. The math produces it. But the deeper physical reason for exactly that angle emerging from the interplay between the ecliptic and galactic planes is still an open question. And the mysteries of the inner Oort cloud run far deeper than a tilt angle. Because in 2003, a discovery in the solar system's outer reaches broke every model scientists had built. An object sitting exactly where nothing should be, moving in an orbit no known force could have produced. On November 14, 2003, astronomer Michael Brown and his team at the California Institute of Technology found something wrong with the solar system. They were scanning the outer solar system with a telescope when they spotted a faint, slow-moving object far beyond Neptune. It was small, reddish in color, and on a very strange orbit. They named it Sedna, after the Inuit goddess of the sea. The numbers on Sedna's orbit made scientists uncomfortable. Sedna orbits the Sun, but its path is extremely stretched. At its closest, it comes to 76 astronomical units from the Sun. That is already more than twice the distance to Neptune. At its farthest, it swings out to around 900 astronomical units. Its orbit takes approximately 12,600 years to complete one lap. This placed Sedna in a strange no-man's land, too far out to have been placed there by Neptune's gravity, which runs out of meaningful influence well before 76 astronomical units. Too close in to be a genuine Oort cloud object, which by the classic model begins at 2,000 astronomical units. Sedna sat in a gap between the two regions, a gap where, according to the standard model, no process could leave a large object. Every explanation scientists had for how small bodies ended up in various orbits failed to account for Sedna. Neptune scattering? Neptune's gravity does not reach that far. The galactic tide? The galactic tide is far too weak to act on objects that close to the Sun. A random passing star in the current era? The math ruled it out. Sedna was sitting in an orbit that the solar system's known mechanics could not produce. Brown's team described it as the most distant object ever found orbiting the Sun at the time of its discovery. And Sedna came with one additional mystery: its color. Oort cloud objects were expected to be grey or white, coated in fresh ice and unprocessed surface material. Sedna is nearly as red as Mars. That redness suggests intense processing by cosmic radiation over enormous timescales, hinting at a history more complicated and more exposed than its distant orbit would normally allow. Sedna immediately generated three competing theories for how it ended up where it is. Scientists are still arguing about it, and Sedna stopped being a lone oddity 11 years after its discovery, when a second object appeared in the same impossible region of space. Sedna broke the standard model of the outer solar system. To explain it, scientists went back to the drawing board and came up with three fundamentally different scenarios. Each one, if true, would rewrite a different piece of solar system history, and so far, none of them has been confirmed. The first explanation is a close stellar encounter early in the solar system's history. When the solar system was young, about 4 billion years ago, stars were closer together on average, and the Sun may have had a temporary neighboring star drift past at relatively close range. Perhaps within a few hundred astronomical units, a star that close would have exerted significant gravitational force on the outer solar system. Its pull could have dragged some objects from the Kuiper belt outward into Sedna-like orbits, detached from Neptune's influence and sitting in that otherwise impossible zone. This explanation is plausible and fits the physics. However, finding any direct evidence of a specific past stellar encounter is essentially impossible at this point. The event would have left no recoverable trace beyond the orbital signatures of objects like Sedna itself. The second explanation is formation inside a dense stellar birth cluster. The Sun was born in a stellar nursery alongside hundreds or thousands of other young stars. Before those stars dispersed into the galaxy, they were packed close enough together that their collective gravity reshaped the outer solar system significantly. In this scenario, Sedna's orbit was pushed into its current shape during that crowded early period, before the Sun's neighborhood thinned out. Simulations support this as physically viable. The third explanation connects to one of the biggest ongoing debates in planetary science. A hypothetical massive planet, sometimes called Planet 9, may be lurking in the deep outer solar system at distances of 500 to 1,000 astronomical units. If it exists, its gravity could have pushed Sedna into its current orbit without requiring any unusual stellar encounters. Each of these three explanations is scientifically serious. Each has supporting simulations and research papers behind it, and each requires something large and unknown to have happened to the solar system that we cannot directly confirm. The orbit of one dwarf planet, sitting in a gap that should be empty, is forcing scientists to confront how little they know about the solar system's early history. And Sedna was only the first warning. For 11 years after Sedna's discovery in 2003, some scientists held out hope that it was a statistical freak, one unusual object in an unusual orbit, a cosmic coincidence. The solar system is old and complex, and strange things happen. Maybe Sedna was just one of them. Then, in 2014, a second object appeared. Astronomers scanning the outer solar system found a body now known as 2012 VP113. It is not as large as Sedna, but its orbit tells the same impossible story. Its closest approach to the Sun sits at about 80 astronomical units. It never comes close enough for Neptune to have put it there. It sits in the same forbidden region, the same gap between the Kuiper belt and the inner Oort cloud, where the standard model of the solar system says nothing should be resting undisturbed. Two objects in the same impossible region is no longer a coincidence. The discovery of 2012 VP-113 confirmed that Sedna is not a freak accident. Sedna is the brightest, most easily spotted member of an entire hidden population of objects, sitting in that transition zone between the Kuiper belt and the inner Oort cloud. Scientists gave this population a name: Inner Oort cloud objects, or the Hills cloud population. Other bodies, named 2004 VN112 and 2010 GBS174, have since been identified as likely members of the same group. The solar system has an entire class of objects that the standard models never predicted. They orbit the Sun. They are too far for Neptune to have placed them there. They are too close for the galactic tide to have shaped them at their current distances. And they are clustered in a way that random chance cannot explain. That clustering is what matters most. Multiple objects in the same region, with orbits pointing in similar directions, suggest a common cause. Something pushed them there, and that something affected all of them in a coordinated way. Two of the three explanations from the Sedna chapter, the stellar birth cluster and the undiscovered planet, both predict this kind of clustering. A one-time stellar encounter would scatter objects more randomly. The fact that multiple inner Oort cloud bodies share similar orbital characteristics points more strongly toward either the Sun's crowded infancy or an ongoing gravitational influence from something still out there. Scientists now actively search for more objects in this region. Every new discovery adds a data point to a map that is still mostly blank. But the inner Oort cloud holds surprises beyond just its unexpected residents, because some of the objects sitting out there, possibly a large fraction of them, did not form in this solar system at all. Here is a possibility that changes everything. A meaningful fraction of our Oort cloud came from other star systems entirely. This is confirmed science, backed by simulations from multiple independent research groups, including a major 2021 study from Leiden University in the Netherlands, and a 2010 paper published in the journal Science. Here is how it works. The Sun was born inside a stellar nursery, a dense cluster of hundreds or thousands of young stars packed closely together over millions of years. During that crowded period, stars were close enough that their protoplanetary disks, the flat spinning clouds of material around each star from which planets and comets form, overlapped or came very close to each other. In that environment, comets and icy objects could transfer between star systems. A body orbiting a neighboring star could get gravitationally nudged, escape that star's grip, drift through space and get captured by the Sun's gravity. Computer models show this transfer would have happened at significant rates during the cluster phase. The 2021 Leiden University simulation, which modeled the full formation history of the Oort cloud from the Sun's birth through the present day, found that up to 50% of the inner Oort cloud material and up to 25% of the outer Oort cloud material could be objects that originally formed around other stars, captured during the Sun's infancy, dragged in by the Sun's gravity while the stars were still packed together, and then frozen in place as the cluster dispersed and the Sun drifted away into open space. This means that when a long-period comet falls into the inner solar system from the Oort cloud, there is a real chance it formed around a completely different star. It spent billions of years orbiting another sun, got captured, traveled outward into our Oort cloud, and has been sitting there ever since, waiting. The chemistry of that comet, the specific mix of ices and dust locked inside it, would carry the signature of its birth star's protoplanetary disk, different from the native material in our solar system. So far, scientists cannot look at an individual comet and confirm it is a captured immigrant rather than a native object. The tools to make that distinction from Earth do not yet exist. But the math says they are out there, mixed in with the native material, indistinguishable from the outside, silent evidence that our solar system spent its first millions of years surrounded by neighbors. Those neighbors may have given us more than just borrowed comets. The Sun did not form alone. Stars almost never do. They are born in groups, inside giant clouds of gas and dust that collapse under their own gravity and fragment into dozens, hundreds, or sometimes thousands of new stars, all igniting within a few million years of each other. Astronomers call these places stellar nurseries, and they are among the most active and chaotic environments in the galaxy. In a stellar nursery, young stars are packed tightly enough that the distances between them are measured in fractions of a light year rather than multiple light years. The Sun's current nearest neighbor, Proxima Centauri, is about 4 light years away. In a typical stellar nursery, the average separation between stars is far less than that. At those distances, the disks of material forming around each young star can interact. Gravitational forces reach across the gap between neighboring stars. Objects in the outer regions of one star's forming disk can get captured by a passing neighbor's gravity, pulled free, and drawn into a new orbit around the other star. The 2010 science paper, led by Harold Levison and colleagues, modeled this process using numerical simulations of stellar clusters with properties similar to the Sun's likely birth environment. The results showed that cometary material transfers between star systems at a high enough rate during this cluster phase to significantly inflate the total population of the Oort cloud beyond what the solar system's own planetesimals could produce alone. This matters because the Oort cloud's total estimated population, somewhere between 1 trillion and 2 trillion objects, is larger than formation models predict from the solar system's own scattered debris. Foreign capture during the cluster phase could help close that gap. After the cluster phase ends, the stars drift apart. Within about 20 to 50 million years of the Sun's birth, the stellar nursery dispersed. The Sun moved into open space. The gap between it and neighboring stars grew to light years, and the exchange of material slowed to almost nothing. The door closed. Whatever had been captured stayed captured. Whatever had been lost was gone. But the captured material remains in the Oort cloud today, frozen, silent, indistinguishable from native objects in almost every way we can currently measure. Scientists found indirect support for this picture from 2 interstellar visitors that passed through the inner solar system in recent years. Objects arriving on paths that curved too sharply to be bound to the Sun, traveling too fast to have originated here. Those objects are part of a bigger story about the traffic between star systems. And the largest known comet ever observed from the Oort cloud has its own story to tell about what the cloud preserves. In 2021, 2 astronomers sifting through old survey data made a discovery that immediately broke records. Pedro Bernardinelli and Gary Bernstein were searching through images from the Dark Energy Survey, a sky mapping project that had photographed large sections of the sky over several years for a completely different purpose, studying how dark energy shapes the large-scale structure of the universe. While analyzing that archive, they spotted a slow-moving object in the outer solar system that had been captured in dozens of images taken over multiple years. They calculated it again. Comet Bernardinelli-Bernstein is approximately 85 miles wide. That is roughly the distance from Los Angeles to San Francisco, folded up into a single icy object hurtling through space. Most known comets are a few miles across at most. The average cometary nucleus is somewhere between 1 and 6 miles wide. This comet is over 10 times larger than the typical comet, a record breaker by a wide margin. Its orbit traces back to the Oort cloud, making it the largest known Oort cloud comet ever observed. When discovered, it was approaching the Sun from far out in the solar system. Scientists calculated its path and found it would reach its closest approach to the Sun at about 10.5 astronomical units, just inside Saturn's orbit, sometime in 2031. Then it would swing back outward, heading away from the Sun for millions of years. This is the comet's first documented visit to the inner solar system. Its orbital period is measured in millions of years. The last time it was anywhere near this close to the Sun, modern humans did not exist. What makes Bernardinelli-Bernstein significant beyond its size is what it represents physically. It has spent billions of years in the deep freeze of the Oort cloud, barely touched by sunlight, barely altered by anything. An object that large, that cold, that pristine, is a direct sample of the early solar system's chemistry, preserved in near-perfect condition. And then in June 2025, something happened that no one expected this far out. The comet woke up early. Scientists using the ALMA radio telescope array in Chile detected something erupting from its surface. While the comet was still at 16.5 astronomical units from the Sun, more than halfway to Neptune, carbon monoxide gas was jetting out from the nucleus in complex evolving patterns. Those jets changed shape between two observations taken just 9 days apart. At 16.5 astronomical units, the temperature is far colder than anywhere on Earth's surface. Solar heating at that distance is a tiny fraction of what Earth receives. Scientists had expected this comet to stay quiet much farther out. The fact that it is already active, already venting frozen gas into space, suggests the comet's interior may be generating activity through mechanisms that do not rely on direct solar heating. A comet this large, this far from the Sun, erupting with carbon monoxide jets, is showing scientists something new about what the Oort cloud actually preserves inside its giant frozen bodies. And this discovery points directly to the next question. What else are those bodies hiding? The ALMA telescope array sits in the Atacama Desert in Chile, at an altitude of over 3 miles above sea level. It is one of the most powerful radio observatories ever built, capable of detecting faint signals from objects billions of miles away. In March 2024, scientists pointed it at Bernardinelli Bernstein. What they found changed what scientists thought they knew about comet activity. At 16.5 astronomical units from the Sun, the temperature around the comet is extraordinarily cold. Colder than liquid nitrogen, colder than anything manufactured on Earth outside a laboratory. At that distance, water ice does not sublimate, it stays frozen. Scientists expected Bernardinelli Bernstein to be completely dormant, a dark, silent boulder drifting through the outer solar system. Instead, ALMA detected carbon monoxide gas erupting from the nucleus in active, structured jets. The jets were not uniform. They came from specific locations on the surface and showed complex, shifting patterns. When scientists compared observations taken 9 days apart, the jets had visibly changed. New venting had started. Carbon monoxide has a much lower sublimation temperature than water. It turns from solid to gas at temperatures far colder than water ice needs. This is why it can be active so far from the Sun, where water ice remains completely frozen. But even accounting for carbon monoxide's lower activation point, the level of activity observed at 16.5 astronomical units was more intense than existing models predicted for a comet at that distance. The leading explanation is that Bernardinelli Bernstein carries an enormous internal reservoir of trapped carbon monoxide, built up over billions of years in the deep freeze of the Oort cloud. As the comet now slowly warms during its first approach toward the Sun, in millions of years, that stored gas is finding pathways to the surface and erupting. This is significant for several reasons. Carbon monoxide is one of the original molecules present in the gas cloud that formed the solar system 4.5 billion years ago. It was among the first ices to condense in the cold outer regions of the protoplanetary disk. An object that has preserved carbon monoxide in its interior since the solar system's earliest days is carrying a direct chemical record of conditions that existed before Earth formed. The evolving jets seen by ALMA also tell scientists something about the comet's interior structure. The fact that venting patterns change dramatically in just 9 days means the comet is responding to its environment in complex ways. The interior is not uniform. Different regions have different compositions, different pressures, different physical structures. For the first time, scientists have direct observational evidence of molecular activity inside a pristine Oort cloud body. Every other comet studied up close has been a short-period comet, one that has made many trips through the inner solar system and lost much of its original surface material over millions of years. Bernardinelli Bernstein is essentially untouched. Its chemistry is as close to original as anything humanity has ever been able to study. What is erupting from its surface is a message from the birth of the solar system itself, and the Oort cloud holds billions more of these frozen time capsules. Some of them have been sitting undisturbed even longer than Bernardinelli Bernstein. 4.5 billion years ago, the solar system was a spinning disk of gas and dust around a newborn sun. The chemistry of that disk varied by distance. Close to the sun, temperatures were too high for most ices to survive. Farther out, in the cold regions beyond what scientists call the frost line, ices of water, carbon monoxide, carbon dioxide, methane, and ammonia condensed onto dust grains and began clumping together. Those clumps grew into planetesimals. The planetesimals collided and merged into larger bodies. The outer planets formed from the largest of them. And the leftover material, billions of smaller icy chunks that never made it into a planet, got scattered outward by the giant planet's gravity into the Oort cloud. That leftover material has been sitting in the cold ever since. The temperature in the Oort cloud is close to 3 degrees above absolute zero. At that temperature, chemical reactions slow to almost nothing. Molecules that froze into those cometary nuclei 4.5 billion years ago are still there today, locked in the same state they were in when the solar system was brand new. This makes Oort cloud objects uniquely valuable as scientific targets. Every comet that has spent time in the inner solar system has been changed by its journey. Solar radiation breaks down surface molecules. Repeated heating and cooling drives off volatile gases. Dust coats the nucleus and alters its chemistry. A short-period comet that has orbited the Sun hundreds of times is a heavily processed, altered body. A long-period comet falling from the Oort cloud on its first visit is different, especially a first-time visitor, one that has never passed through the inner solar system before. Its surface layers may have been altered by cosmic rays over billions of years, but its interior remains pristine. The ices locked inside it are essentially unchanged from the day the solar system formed. Scientists can use the chemistry of these fresh comets to reconstruct conditions in the protoplanetary disk. The ratio of different isotopes of hydrogen, carbon, and oxygen in the ice tells scientists about the temperature and pressure where the comet originally formed. The types of organic molecules present reflect the chemistry of the gas cloud that collapsed to form the Sun. The structure of the dust mixed into the ice preserves information about the processes that built the first solid bodies in the solar system. Every long-period comet is a frozen data package sent from the beginning of time, arriving in our sky for scientists to read. And occasionally, a comet arrives that has never been here before at all, making its first pass through the inner solar system after millions of years of travel. Its story is different from every comet that came before. In March 2024, a team discovered a comet with an orbital history unlike almost any other. They named it Comet Virchow, after one of the astronomers who found it. When scientists traced its path backward through the equations of gravity, they found something remarkable. This comet is making its first known passage through the inner solar system. Its orbital period is measured in millions of years. The math of its orbit indicates it has been traveling in the deep outer solar system since long before modern humans existed. Its last approach anywhere near the Sun, if it ever made one, predates recorded history by an almost incomprehensible margin. First-time visitors from the Oort cloud are scientifically precious. A comet that has made the inner solar system circuit many times has been cooked, blasted by radiation, and stripped of its most volatile surface layers. Each pass near the Sun removes some of the original material. After enough trips, what remains is a processed remnant, still interesting, but no longer representative of its original state. A first-time visitor has never experienced any of this. Its surface, except for the outermost layers altered by billions of years of cosmic radiation in the Oort cloud, is as close to original as possible. The volatile ices that would have boiled away on any repeat visitor are still there, locked in. Scientists can observe the comet's outgassing behavior as it warms for the first time and gather data that no processed comet can provide. First-time visitors also carry direct information about the Oort cloud itself. Their original orbits, calculated by tracing their paths backward before they enter the planetary system's gravitational influence, point precisely to the region of the Oort cloud they came from. The direction of arrival, the shape of the incoming orbit, and the estimated size of the comet together build a data point in the map of where Oort cloud objects are distributed. Every first-time visitor is a probe that the Oort cloud launched itself, carrying information about its home region. They arrive unpredictably. Scientists cannot schedule them. They appear in survey data without warning. identified by their slow movement and their extreme orbits. And each one brings a story of a journey so long that the universe was measurably different when it began. A comet that left the Oort cloud millions of years ago, when it was nudged by a passing star or the galactic tide, has been falling toward the sun across a distance so vast that light itself takes years to cross it. And while it was falling, everything on Earth changed beyond recognition. The timescales involved in the Oort cloud make the human story look very small. A school year is about 10 months. A human lifetime, if things go well, is around 80 to 90 years. The Roman Empire lasted roughly 500 years. Humans have existed as a species for somewhere around 300,000 years. Some comets in the Oort cloud take 30 million years to complete a single orbit around the sun. Put that number against human history, and it stops making sense in a normal way. When a long-period comet last passed through the inner solar system 30 million years ago, the ancestors of modern elephants were small, pig-sized creatures. The Himalayas were still rising. The continents looked subtly but meaningfully different from today. The Atlantic Ocean was narrower. All of that happened, all of that changed, in the time it took this comet to swing out to the Oort cloud and come back. These extreme orbits are a direct consequence of the forces acting on Oort cloud objects. When a comet gets kicked out of the Oort cloud and falls toward the sun, it arrives on a highly elliptical orbit, stretched out into a long, thin needle shape. Its closest approach to the sun might be inside Earth's orbit. Its farthest point swings back out to tens of thousands of astronomical units. The farther that outer point is, the longer the orbit takes. An object with an outer turning point at 100,000 astronomical units from the sun has an orbital period that stretches into the tens of millions of years. These comets spend the overwhelming majority of their orbital time in the cold outer solar system, invisible, moving almost imperceptibly slowly. Then, as they curve back toward the sun, they accelerate. By the time they reach the inner solar system, they are moving at dozens of miles per second. They pass through quickly, just months or a few years near the sun, developing bright tails of gas and dust. Then they swing around the sun and head back outward. And then they are gone for another geological age. Every long-period comet visible from Earth is carrying the record of its journey embedded in its orbit. Scientists calculate where it came from, how long it has been traveling, and whether this visit to the inner solar system is its first or one of many. The sheer scale of those timescales is one reason the Oort cloud feels so alien. The physics is the same physics governing everything else in the solar system, the same gravity and momentum and orbital mechanics. But the timescales stretch so far beyond anything human that the Oort cloud operates almost outside of time, by any human measure. And yet the Oort cloud connects to human history in one of the most disturbing ways imaginable. The Oort cloud does not stay perfectly still. The galactic tide works on it constantly. Passing stars occasionally come close enough to stir its outer edges. And periodically, something more dramatic happens. Scientists studying the history of the inner solar system identified a disturbing pattern. At irregular intervals, the rate of large comet impacts in the inner solar system appears to spike. A sudden surge of long-period comets arriving in tight clusters rather than the steady trickle seen in quieter periods. Scientists call these events comet showers. During a comet shower, the number of Oort cloud objects falling into the inner solar system increases dramatically. The probability of a large body hitting Earth or another planet rises accordingly. A comet shower can last several million years. Elevated impact rates sustained over geological time rather than a single event. What causes them? Several mechanisms can trigger a comet shower. A close stellar flyby, a star passing within a few thousand astronomical units of the sun, can gravitationally shake the outer Oort cloud and send a wave of displaced objects falling inward. Stars come this close to the sun roughly once every few 100,000 years on average, though the timing varies. Passage through a giant molecular cloud, an enormous region of dense gas in the galaxy, can similarly disturb the Oort cloud. These clouds are scattered throughout the Milky Way, and the solar system passes through or near them occasionally as it orbits the galaxy. Both of these triggers are essentially random, hard to predict, and leave no regular cycle in the impact record. But a third proposed trigger is different. It could produce a repeating rhythm. the Sun does not travel in a perfectly flat path through the Milky Way. It oscillates up and down through the galactic plane, like a horse on a carousel, bobbing above and below the flat disk of the galaxy on a long, slow cycle. As it dips toward the galactic midplane, it enters a region of higher stellar density and stronger galactic tidal forces. The Oort cloud experiences stronger perturbations, more objects fall inward. That oscillation cycle has a period of roughly 30 to 35 million years from peak to peak, and scientists, examining the geological and fossil record, found something that matched. The Milky Way galaxy is a flat disk, but the Sun does not sit still within it. The Sun orbits the galactic center, taking about 225 million years to complete one full circuit around the galaxy. During that journey, it also bobs up and down through the galactic plane, repeatedly crossing through the densest, most crowded region of the disk. This vertical oscillation has a period of roughly 30 to 35 million years. Every 30 to 35 million years, the Sun passes through or near the galactic midplane, where stars, gas clouds, and dark matter are most densely concentrated. Near the midplane, the galactic tide gets stronger. The gravitational pull from all that mass tugs harder on the loosely bound objects in the outer Oort cloud. More objects get perturbed. More comets fall inward toward the inner solar system. Scientists studying the fossil record found something striking. Mass extinction events on Earth show a statistical clustering with a cycle of approximately 31 million years. The timing is imprecise. The correlation is not perfect, but the pattern is real enough that multiple researchers have published studies on it. The hypothesis connecting these two facts is straightforward. When the Sun crosses the galactic midplane, the Oort cloud gets shaken. A comet shower follows over the next few million years. The increased impact rate raises the probability of a large cometary body hitting Earth, and occasionally one does, with consequences severe enough to drive mass extinctions. This is a theory, not confirmed science. The chain of cause and effect between galactic oscillation, Oort cloud disturbance, comet shower, Earth impact, and mass extinction involves multiple steps, each with its own uncertainties. Scientists at the University of Washington published research in 2009 finding that comet impacts alone are unlikely to explain every major mass extinction event. Other factors, volcanic activity, sea level changes, climate shifts, almost certainly played roles. But the Oort cloud remains a plausible contributor to the periodic rhythm of life and death on Earth. Our solar system is not floating in a static, quiet universe. It is a moving object inside a living galaxy, and the galaxy reaches in and shakes the frozen shell around our solar system every 30 million years or so. What happened the last time the shake was strong enough to matter? 66 million years ago, something struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact crater, called Chicxulub, is about 110 miles wide. The energy released was billions of times greater than any nuclear weapon ever built. The impact triggered fires, tsunamis, and a debris cloud that blocked sunlight globally for months or years. The non-avian dinosaurs went extinct. So did about 3/4 of all species on Earth. The object that caused this was most likely an asteroid, a rocky body from the inner solar system. That is the scientific consensus, based on the chemical signature of the impact layer found worldwide, which matches asteroid composition more closely than cometary composition. However, the case is not completely closed, and a minority of researchers continue to argue for a cometary origin or a combined scenario. The hypothesis connecting this extinction to the Oort cloud works as follows. If the Sun was near the galactic midplane roughly 66 million years ago, which the orbital math roughly supports within its uncertainties, the resulting increase in galactic tidal forcing could have triggered a comet shower. That shower would have elevated impact rates across the inner solar system for several million years. While the Chicxulub impactor may have been an asteroid, a cometary shower could have indirectly increased the overall rate of disturbances in the asteroid belt as well, nudging more rocky bodies onto Earth-crossing paths. This indirect pathway is speculative. Scientists are careful to distinguish between the confirmed impact event at Chicxulub and the unconfirmed hypothesis of a galactic trigger behind it. What the research does confirm is this. Large impacts have shaped the history of life on Earth multiple times. The solar system is not a sealed, safe environment. It receives disturbances from outside, from passing stars, from galactic forces, and from the vast frozen reservoir at its outer edge. The Oort cloud is not just an astronomical curiosity. Its behavior over millions of years has a direct relationship to which species survive and which vanish on a small rocky planet 30 astronomical units from its inner edge. And right now, there may be an undiscovered planet actively reshuffling the Oort cloud's contents. In 2016, two Caltech astronomers named Michael Brown and Konstantin Batygin published a paper arguing that something large and undiscovered is lurking in the deep outer solar system. They called it Planet 9, and they estimated it has a mass roughly 5 to 10 times that of Earth, orbiting somewhere between 500 and 1,000 astronomical units from the Sun. Planet 9 has never been directly observed. Its existence is inferred from the orbital behavior of a group of small distant objects in the outer solar system, whose paths cluster together in a way that probability alone cannot explain. The clustering, according to Brown and Batygin's analysis, strongly suggests a massive gravitational influence shaping those orbits from a consistent direction. If Planet 9 is real, its consequences for the Oort cloud are significant. Simulations published in 2021 showed that a planet of this mass at this distance would not just sculpt the Kuiper belt. Its gravity would act on the inner Oort cloud as well, pumping objects between the inner Oort cloud and the scattered disk, the region of smaller bodies beyond Neptune. It would blur the boundary between these two populations, creating a mixed zone where objects originally from the inner Oort cloud are pushed inward and objects from the scattered disk are pushed outward into Oort cloud orbits. Planet 9 would also alter the populations of long-period comets reaching the inner solar system. Some comets that scientists currently assume originated in the outer Oort cloud may actually be inner Oort cloud objects that Planet 9 displaced. The statistics scientists use to estimate the Oort cloud's population and structure depend on assumptions about where comets come from, and Planet 9 would scramble some of those assumptions. In 2024, new evidence came from icy bodies found on Neptune crossing orbits, whose inclinations cluster in a way that is difficult to explain without a massive distant perturber. This is consistent with Planet 9's predicted influence. The inner Oort cloud has been treated for decades as a frozen, dynamically stable archive. Planet 9, if it exists, is a hidden key that may have been reorganizing that archive continuously since the solar system formed. Whether it exists or not remains one of the most significant unanswered questions in planetary science, and the boundary between the Oort cloud and the rest of the solar system is proving far harder to define than anyone expected. Draw a line from the Sun outward. For 30 astronomical units, you are in the planetary zone. From 30 to maybe 50 or 60 units, you pass through the Kuiper belt, a flat ring of icy objects beyond Neptune. Then there should be a gap, a mostly empty stretch, before the inner Oort cloud begins at around 2,000 units. That is the textbook picture. Clean borders, distinct regions, neat categories. Sedna demolished it. At 76 astronomical units at closest approach and 900 units at farthest, Sedna sits squarely in the supposed gap. 2012 VP 113 does the same. So do several other recently identified objects. They occupy territory the standard model said should be mostly empty. Astronomers now recognize that the boundary between the outer Kuiper belt, the extended scattered disk, and the inner Oort cloud is not a clean line. It is a gradient, a region of transition where different populations overlap and blend into each other. Objects in this zone have been placed there by a variety of mechanisms, some by Neptune's gravity, some by the galactic tide acting over billions of years, some possibly by Planet 9 or past stellar encounters. The definitions themselves have become blurry. Scientists debate exactly where the Kuiper belt ends and the inner Oort cloud begins, and the answer depends partly on which definition of those regions you use. This blurriness is scientifically important because it means the populations are connected. Objects do not stay permanently in one region. They get nudged by Neptune, pushed by the galactic tide, or perturbed by a passing star and moved from one zone to another over geological time. The Kuiper Belt, the scattered disk, and the inner Oort cloud are not three separate reservoirs. They are three zones in a continuum, with material flowing slowly between them over billions of years. Every time a survey finds a new object in the transition zone, it fills in one more data point in a map that scientists are still building. The Vera Rubin Observatory, a powerful new telescope that began full survey operations in the 2020s, is expected to dramatically expand the catalogue of known objects in this entire outer region. Its wide-field camera and regular sky surveys make it ideal for catching slow-moving, faint bodies in the transition zone. But the true Oort cloud, the region beyond several thousand astronomical units, remains completely beyond the reach of any instrument humanity has ever built or planned. The Hubble Space Telescope can photograph galaxies billions of light-years away. The James Webb Space Telescope can detect the atmospheres of planets orbiting other stars. The Vera Rubin Observatory can survey the entire visible sky every few nights, catching objects that move between images. None of them can see a confirmed Oort cloud object sitting in its home region. The problem is physics. A typical Oort cloud cometary nucleus is somewhere between a half-mile and 5 miles wide. At distances of 10,000 to 100,000 astronomical units, detecting an object that small would require collecting an amount of reflected sunlight so tiny it falls orders of magnitude below the detection threshold of any telescope ever built. The James Webb Space Telescope, the most powerful space telescope humanity has ever launched, cannot come close to detecting an Oort cloud object at its actual distance. There is a second problem: movement. Telescopes detect objects in the outer solar system by watching them move against the background of distant stars between multiple exposures taken days or weeks apart. The closer an object is, the faster it appears to move. Objects in the Kuiper Belt, at 30 to 50 astronomical units, move fast enough to be detected with existing survey methods. Oort cloud objects at thousands of astronomical units move so slowly they appear essentially stationary over human observation timescales. Distinguishing them from background stars would require comparing images taken years apart with extraordinary precision. Both the brightness problem and the motion problem would need to be solved simultaneously to directly detect a genuine Oort cloud object at home. Even the discoverers of the 2025 spiral structure acknowledged this directly. They described the prospect of confirming the spiral observationally as having extremely low odds with any foreseeable technology. Their discovery is entirely model-based, derived from the physics of known gravitational forces acting over solar system history, not from imaging actual Oort cloud objects. Everything known about the Oort cloud, its shape, its population, its spiral arms, its foreign material, its connection to the galactic tide, all of it rests on indirect evidence and computational physics. The Oort cloud is the largest structure in the solar system and the least directly observed. This constraint will likely hold for a very long time. Seeing the Oort cloud directly requires either revolutionary telescope technology far beyond anything currently planned, or a spacecraft that travels to the cloud itself. That spacecraft is theoretically possible, but the journey would be unlike anything humanity has ever attempted. The Vera Rubin Observatory sits on a mountaintop in Chile, at an altitude of about 8,800 feet, under some of the clearest, darkest skies in the southern hemisphere. Its primary mirror is 27.5 feet across. Its camera is the largest digital camera ever built for astronomy, capturing an area of sky roughly 40 times the size of the full moon in a single exposure. Every few nights, it photographs the entire accessible sky. Over 10 years of planned operation, it will build a record of every detectable moving object in the solar system, cataloging their positions, brightnesses, and paths across dozens or hundreds of repeated observations. The Vera Rubin Observatory cannot reach the true Oort cloud. Genuine Oort cloud objects at 10,000 astronomical units or more remain invisible. But the transition zone between the Kuiper Belt and the inner Oort cloud, from roughly 100 to a few thousand astronomical units, sits within its potential reach for the larger, brighter objects. Scientists expect the observatory to dramatically expand the catalogue of known objects in the extended scattered disk and the inner Oort cloud transition region. Every new object found in this zone is a data point that constrains models of how the region formed and what forces shaped it. Finding more Sebna-like objects at extreme distances would help determine whether the clustering seen in known objects is statistically robust and whether a massive distant planet is needed to explain it. The observatory is also expected to discover many new long-period comets, first-time visitors from the Oort cloud, that are still far from the Sun when detected. Currently, most long-period comets are discovered only after they have already entered the inner solar system and begun outgassing visibly. Vera Rubin's sensitivity could catch them farther out, providing longer lead times for observation and more data on their original orbits before planetary gravity alters their paths. Each new discovery from this observatory will fill in the blank spaces on the map of the outer solar system. The transition zone between the Kuiper belt and the inner Oort cloud will gradually become better defined, populated with known objects rather than theoretical predictions. The telescope cannot take science all the way to the Oort cloud, but it can bring the edge of the Oort cloud closer to science than it has ever been before. And what lies at the true outer edge of the Oort cloud is more extraordinary than most people realize. Proxima Centauri is the closest star to our Sun. It sits about 4.2 light-years away. 1 light-year is roughly 6 trillion miles. Multiply that by 4.2, and you have the distance to the nearest neighbor in the stellar neighborhood. The outer edge of the Oort cloud sits between 2 and 3 light-years from the Sun. That means the Sun's gravitational territory, the outermost boundary of our solar system, reaches roughly halfway to the nearest star. Our solar system is not a compact object surrounded by empty space. It is an enormous sphere of influence extending most of the way across the gap to the next star system. At 3 light-years from the Sun, an Oort cloud object is so far away that sunlight takes 3 years to reach it. The Sun, viewed from that distance, is just a bright star among thousands, indistinguishable from other stars by eye alone. The object is barely held by the Sun's gravity. A slight gravitational nudge from almost any direction could break that feeble bond and send it drifting into true interstellar space. Objects at the outer edge of the Oort cloud are perched on the edge of belonging to the solar system at all. They are technically bound, technically orbiting the Sun, but barely. Their loyalty to the Sun is marginal. This extreme reach of the solar system has an important implication for what happens when another star comes close. Stars do not stay fixed. They move through the galaxy, drifting relative to one another over millions of years. The Sun has neighbors that drift past it over geological time, not close enough to enter the planetary system, but close enough to interact with the Oort cloud. When a star passes within a few light-years of the Sun, it does not need to come anywhere near the planets to have an effect. Its gravity reaches into the outer Oort cloud and disturbs the loosely bound objects there. It can send a wave of comets falling inward toward the Sun, potentially triggering a comet shower that elevated impact rates persist for millions of years. The nearest star is already close enough to have its gravity reach across the gap and touch the edge of our solar system. And if our Oort cloud extends almost halfway to the nearest star, and that star has its own similar cloud, something remarkable follows. The Sun has an Oort cloud. There is no reason to believe it is unique. Every star that formed in a stellar nursery went through the same process the Sun did. Gas and dust collapsed. A star ignited. A protoplanetary disk formed. Planets or failed planets grew, scattering leftover debris outward. Galactic tidal forces gradually rounded those scattered bodies into a spherical shell. Scientists expect every star with a significant planetary system to have its own equivalent of the Oort cloud, a reservoir of icy, loosely bound debris surrounding it at enormous distances. These structures are called exo-Oort clouds, meaning Oort clouds belonging to other stars. No exo-Oort cloud has ever been directly observed. They are as invisible around other stars as our own Oort cloud is invisible from Earth. But the physics strongly supports their existence, and there is indirect evidence for it from the interstellar objects that have passed through our solar system. Here is where the geometry becomes remarkable. Our Oort cloud extends roughly 2 to 3 light-years from the Sun. The nearest star, Proxima Centauri, is 4.2 light-years away. If Proxima Centauri has its own cloud of similar extent, the two clouds reach toward each other across a gap of barely more than 1 light-year. They may already overlap. The overlapping zones of two stellar Oort clouds would create a region where objects from both systems occupy the same space. Objects could drift between the two systems over millions of years. Material originally formed around one star could eventually find itself loosely captured by the other, a very slow, very diffuse form of exchange between neighboring star systems. This concept, that neighboring stellar systems are embedded in overlapping halos of loosely bound icy debris, suggests the space between stars is populated, however sparsely, with objects from many different origins. The gap between stars is less empty than it looks, and two objects have already confirmed that traffic between stellar systems is real. In October 2017, a telescope in Hawaii detected a faint, fast-moving object crossing through the inner solar system. Scientists calculated its orbit and found something that had never been confirmed before. The object was moving too fast and on too sharply curved a path to be gravitationally bound to the Sun. It came from outside the solar system entirely. They named it Oumuamua, a Hawaiian word meaning something like distant messenger arriving first. Oumuamua was strange in almost every way. Its brightness varied dramatically as it rotated, suggesting an unusual shape, either extremely elongated or flat like a pancake. It appeared to be tumbling, and as it left the solar system, it accelerated slightly beyond what gravity alone could explain, a push that the best current explanation attributes to outgassing of material from its surface, though the specifics remain debated among scientists. In 2019, a second interstellar visitor arrived. This one, named Borisov after the amateur astronomer who discovered it, was much more recognizable. Borisov was an active comet, clearly outgassing as it swung through the inner solar system with a composition that matched solar system comets closely enough to confirm that cometary chemistry is probably similar across many different stellar systems. Both objects were traveling on paths that originated in interstellar space. Both were moving through the solar system on one-way trips, coming from the direction of one part of the galaxy, curving around the Sun, and heading off toward another region of space forever. The leading scientific explanation for where objects like these come from points directly at exo-Oort clouds. Other stellar systems shed material from their outer clouds constantly, objects perturbed by passing stars or galactic tides, and sent drifting through interstellar space on long, slow journeys between the stars. The galaxy is likely threaded with this debris. Comets and asteroids ejected from dozens or hundreds of stellar systems over billions of years. Our solar system moves through that interstellar debris field every day. Oumuamua and Borisov were the first two we caught in the act. Scientists estimate that interstellar objects like these may pass through the solar system far more frequently than two detected objects would suggest. Most are simply too small, too dark, and moving too fast to be caught by current survey instruments. The Sun is constantly sailing through material from other stellar systems, and the Sun is constantly shedding material of its own into the interstellar medium as well. The Sun has been orbiting the center of the Milky Way for 4.5 billion years. That is roughly 20 full circuits around the galactic center, each taking about 225 million years. The Sun does not travel alone. It carries its planets, its Kuiper belt, and its Oort cloud with it through the galaxy. But not everything stays with the Sun. The 2021 Leiden University simulation of the Oort cloud's full formation history predicted something striking. During the process of Oort cloud formation, billions of planetesimals were flung outward from the early solar system. Most were captured into Oort cloud orbits. Some were ejected entirely, sent beyond the Sun's gravitational reach into interstellar space. Those ejected objects did not stop. They kept moving. They entered the interstellar medium and continued traveling in roughly the same direction and at roughly the same speed as the Sun was moving at the time of their ejection. Over billions of years, this creates a diffuse stream of solar system debris, trailing the Sun's path through the galaxy, and extending ahead of it as well from objects ejected during earlier portions of its orbit. Scientists call this structure a cometary contrail, using the analogy of the vapor trail left behind a jet aircraft. The Sun's orbital path through the Milky Way, over 4.5 billion years, may be marked, however faintly, by a trail of objects it shed during Oort cloud formation. This contrail, if real, would be detectable in principle. Objects in the contrail would have velocities and orbital characteristics that mark them as former solar system members. Similar in composition to known comets but moving through interstellar space on paths tracing the Sun's past trajectory through the galaxy. Finding such objects would require surveys sensitive enough to detect small, dark objects moving through the interstellar medium, far beyond current capabilities. But the prediction exists, and it represents one of the more extraordinary ideas to emerge from Oort cloud research. The Sun has been writing its autobiography across the Milky Way for 4.5 billion years, leaving a faint trail of frozen debris as its signature. Every orbit around the galaxy, a small record of where it has been. And all of this, every discovery, every theory, every frozen comet in the dark, points back to the same question: what does any of this mean for the planet you are living on right now? Pull back from everything covered so far: the trillion-body frozen shell, the spiral arms, the stolen material, the galactic tide, the comet showers, the 31 million year cycle, the blurred edges, the impossibly distant first-time visitors, the interstellar traffic. All of it connects back to a single point in space: Earth. The Oort cloud is the solar system's long-term memory and its most significant external threat reservoir. Every large comet that has ever darkened Earth's skies, that has ever contributed to a mass extinction, that has ever altered the trajectory of life on this planet, came from the Oort cloud, or was disturbed by forces that also disturbed the Oort cloud. The same galactic tide that sculpted the spiral arms in the inner Oort cloud also periodically stirs the outer cloud. The same galactic oscillation that produces the 31 million year rhythm in the Oort cloud's disturbance rate also appears in the fossil record as a clustering of extinction events. This planet's biological history is connected, however partially and uncertainly, to the physics of objects sitting hundreds of thousands of astronomical units away. This is confirmed science. Mass extinction events show a statistical correlation with the Sun's galactic oscillation cycle. The mechanism remains a theory. The correlation is real. There is also a forward-looking dimension. The Sun will continue to oscillate through the galactic plane. It will continue to encounter passing stars. It will continue to receive gravitational nudges from the galaxy's mass distribution. The Oort cloud will continue to be disturbed. Long-period comets will continue to fall inward at some rate. Most will miss Earth. The solar system is mostly empty space, but the probability is never zero. A comet several miles across striking Earth at tens of miles per second would be a civilization-altering event. The Oort cloud contains objects orders of magnitude larger than the typical comet nucleus. Bernardinelli Bernstein, at 85 miles wide, would cause damage on a scale incompatible with anything in recorded human history if it struck Earth. The 2025 discovery of the spiral arms adds new precision to our picture of how the inner Oort cloud is organized and how comet showers might develop. Better models of the spiral structure will eventually lead to better predictions of which regions of the inner cloud are most susceptible to perturbation, and therefore most likely to produce comet showers in the future. And the search for Planet 9 matters here too. If Planet 9 exists and is actively reshuffling inner Oort cloud material, knowing its properties and orbit would dramatically improve scientists' ability to predict long-term comet flux into the inner solar system. The Oort cloud seemed boring for 75 years, a quiet, featureless bubble of frozen junk at the edge of the solar system, beyond reach, beyond observation, beyond relevance to daily life. The discoveries of the past few years revealed something fundamentally different. A dynamic galactic scale structure with spiral arms, foreign material, a direct connection to the history of life on Earth, and ongoing processes that tie the fate of our planet to forces operating across the entire Milky Way. The frozen graveyard at the edge of our solar system has been watching over us since before the first cell divided in the early ocean. And it is still out there now, slowly stirring in the dark.